You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. The history of artificial intelligence is best understood as a long and winding journey, filled with bold visions, dramatic setbacks, and astonishing breakthroughs. By tracing its development, we can see how ideas that began as philosophical questions evolved into some of today's most advanced technologies. From Alan Turing's theoretical foundations to the rise of transformers that power modern generative AI, each stage represents a shift in both technical capability and human imagination. Understanding this history is not merely academic. It allows us to see why AI has developed the way it has, why some methods succeeded where others faltered, and why current debates often echo arguments made decades ago. Looking back also provides humility, reminding us that the field's progress has always been uneven, marked by periods of optimism, disillusionment, and renewal. The story begins with Alan Turing, whose work in the mid-20th century laid the conceptual groundwork for machine intelligence. In his famous paper, Computing Machinery and Intelligence, he posed the provocative question, can machines think? Rather than attempt a philosophical definition of thought, he proposed the imitation game, now known as the Turing Test. The test suggested that if a machine could convincingly imitate human conversation, then, for practical purposes, it could be considered intelligent. This idea reframed the discussion from abstract speculation to observable behavior. Turing's work inspired generations of researchers, not only by introducing the possibility of machine intelligence, but also by providing a concrete framework for evaluating progress. Even today, the Turing test continues to influence debates about AI's capabilities and limitations. During the 1940s and 1950s, the early computer era saw researchers experimenting with machines capable of performing symbolic logic and simple problem-solving. These efforts were fueled by the rise of programmable digital computers, which allowed scientists to explore whether reasoning processes could be expressed as algorithms. Projects like logic machines and early chess-playing programs demonstrated that computers could manipulate symbols and follow rules to reach conclusions. Although rudimentary, these experiments proved that aspects of reasoning could be mechanized. They also attracted excitement from researchers who believed that a path toward general intelligence was within reach. This period was marked by an intoxicating sense of possibility. With computers emerging as more than just calculators, they were potential partners in reasoning. The Dartmouth Conference of 1956 is widely recognized as the birth of artificial intelligence as a formal research field. Organized by John McCarthy and others, the conference brought together leading thinkers to explore the bold proposition that every aspect of learning, or any other feature of intelligence, can in principle be so precisely described that a machine can be made to simulate it. The participants laid out ambitious research agendas, envisioning rapid progress toward machines capable of general intelligence. The Dartmouth meeting set a tone of optimism and established AI as a distinct academic discipline. Its influence cannot be overstated. It provided a shared identity for researchers and ignited decades of exploration into how machines could learn, reason, and solve problems. The 1960s and 1970s were dominated by symbolic AI, also known as good old-fashioned AI. Researchers focused on creating rule-based systems and expert programs that relied on logical representations of knowledge. The idea was straightforward. If you could encode enough facts and logical rules, the machine could draw inferences and act intelligently. For example, programs were developed to solve algebra problems or navigate mazes by following predefined rules. While these systems could perform well in constrained environments, they struggled with ambiguity, incomplete data, and the unpredictability of the real world. Nonetheless, symbolic AI represented a crucial step, demonstrating that computers could mimic aspects of reasoning and problem-solving, even if only within carefully structured domains. This period was also characterized by intense optimism. Many researchers believed that human-level intelligence was just around the corner. Predictions were made that within a decade, machines would surpass human abilities in most areas. Grants and funding flowed into AI research, driven by the belief that breakthroughs were imminent. This optimism reflected both the enthusiasm of pioneers and the novelty of the field, which made it easy to underestimate the complexity of human cognition. While these bold predictions were not realized, they highlight the ambition that has always been part of AI's identity. The dream of building intelligent machines has long been fueled as much by imagination as by incremental progress. The unfulfilled promises of early AI eventually led to disappointment, resulting in what came to be known as AI winters. During these periods, funding was cut, public interest waned, and researchers struggled with the technical limitations of their methods. Symbolic systems proved brittle outside of narrow domains, and computing power was insufficient to support more ambitious approaches. Governments and organizations that had once been enthusiastic scaled back their investments, concluding that AI had overpromised and underdelivered. These winters serve as reminders that hype cycles are not unique to the modern era. They illustrate how the gap between expectations and reality can stifle progress, even when underlying ideas still hold potential. Despite setbacks, the 1980s witnessed the rise of expert systems, a form of commercial AI that found adoption in industries such as medicine and business. These systems encoded human expertise into vast sets of rules, enabling them to provide diagnostics or recommendations in specialized domains. One famous example, MyCIN, was developed to assist with medical diagnoses and treatments. Businesses used similar systems to guide decision-making and improve efficiency. Although expensive to build and maintain, expert systems demonstrated AI's practical utility and rekindled interest in applied research. They also highlighted the value of embedding human expertise into digital tools, paving the way for the next wave of innovation. As the 1980s gave way to the 1990s, researchers began to shift from rigid rule-based systems to statistical methods in machine learning. Instead of encoding every rule explicitly, systems were trained to recognize patterns from data. This approach reflected the growing realization that intelligence might emerge from exposure to examples rather than handcrafted logic. Methods such as decision trees, Bayesian inference, and clustering began to gain traction. These advances were supported by improvements in computing and a broader availability of datasets. The shift marked a turning point, moving AI closer to the adaptive and probabilistic nature of human learning, and setting the stage for more flexible and powerful models. Neural networks, first inspired by biological brains in the mid-20th century, experienced a revival during this period thanks to the development of backpropagation. This algorithm allowed multi-layered networks to adjust their internal parameters efficiently, making them more effective learners. Combined with improved computing power, neural networks began to show promise in tasks like handwriting recognition and speech processing. Although still limited by data and hardware constraints, this revival re-established neural networks as a viable path for AI research. It demonstrated that learning from examples could yield impressive results, and it hinted at the potential for even greater breakthroughs if computational resources continued to expand. The growth of computational power in the late 20th century further propelled AI forward. Faster processors, increased memory, and advances in parallel computing allowed researchers to experiment with more complex models. Tasks that once took hours could now be completed in minutes, opening the door to larger-scale experiments. This growth was not just incremental, it fundamentally changed what was feasible. For example, training neural networks on large datasets became possible, enabling performance leaps that had once seemed out of reach. Computational advances provided the infrastructure necessary for AI to move from small-scale academic experiments to practical applications with real-world impact. The rise of big data in the 2000s transformed AI yet again. With the explosion of digital storage and the Internet, unprecedented volumes of data became available for training. Search engines, social media, and e-commerce platforms all generated vast streams of information. This abundance of data made it possible for machine learning algorithms to detect patterns with greater accuracy and robustness. For instance, recommendation systems became more effective because they could analyze millions of user interactions. Big data not only improved existing models but also encouraged new ones, creating a virtuous cycle where more data enabled better AI, which in turn generated even more data. Deep learning breakthroughs in the 2010s marked another leap forward. Convolutional neural networks, in particular, revolutionized computer vision by enabling machines to recognize images with near-human accuracy. Similar advances occurred in speech recognition, where AI systems began to rival human transcription in controlled environments. These breakthroughs were not isolated. They reflected the culmination of decades of research combined with the availability of big data and modern hardware. The successes of deep learning demonstrated the power of scaling. By stacking layers and training on vast datasets, machines could achieve levels of performance once thought unattainable. This era signaled the arrival of AI systems capable of handling tasks with remarkable sophistication. Milestones in game-playing AI provided some of the most visible demonstrations of progress. In 1997, IBM's Deep Blue defeated world chess champion Garry Kasparov, proving that machines could outplay humans in a highly complex domain. 2 decades later, DeepMind's AlphaGo achieved a similar feat in the game of Go, a challenge far more intricate than chess, due to its astronomical number of possible moves. These achievements captured public imagination, showing that AI could surpass human experts in fields once thought resistant to computation. They also provided valuable testbeds for research, pushing algorithms and computing resources to their limits while inspiring new directions in learning and strategy. Natural language processing also advanced significantly during this time. Early chatbots like Eliza demonstrated basic conversational patterns, but their limitations were obvious. Progress accelerated with statistical models and later neural approaches, culminating in transformer-based architectures that could generate coherent, human-like text. These systems moved beyond simple pattern matching to capturing context, nuance, and even creativity in language use. Transformer models became the backbone of modern AI applications, from translation tools to virtual assistants, highlighting just how far natural language processing had come. The shift in language technology illustrated AI's ability to move from rigid scripts to flexible, data-driven understanding. All of these developments contribute to today's rapid acceleration in AI research. Academic breakthroughs and industry investment feed into each other, creating a cycle of exponential growth. Universities push the boundaries of theory, while companies apply discoveries at scale, generating data and resources that fuel further exploration. This synergy has made progress faster and more visible than at any point in AI's history. The trajectory from Turing to transformers is a testament to persistence, adaptation, and the cumulative nature of innovation. It shows us that AI is not a sudden invention but the result of decades of iteration, setbacks, and triumphs, with each generation building on the last. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Another major driver of progress has been the rise of cloud computing. Training modern AI models requires immense processing power and memory, resources not available to most organizations a decade ago. Cloud services changed that equation by offering scalable infrastructure on demand. Researchers could now rent time on powerful servers rather than building their own. This shift enabled the training of massive models with billions of parameters, something unimaginable in earlier eras. Cloud computing also facilitated deployment, allowing companies to integrate AI into products and services at scale. Whether running recommendation engines for e-commerce or voice recognition for virtual assistants, cloud platforms made AI not only more powerful, but also more practical and cost-efficient for businesses of all sizes. Computer vision, long considered one of the most difficult challenges in AI, made dramatic leaps forward thanks to image recognition benchmarks. Datasets such as ImageNet provided standardized tests that spurred competition among researchers and encouraged creative approaches. Teams worldwide competed to achieve higher accuracy rates, and each incremental improvement pushed the field forward. Convolutional neural networks proved especially effective, setting records in classification tasks and inspiring new architectures. The visibility of these benchmarks gave the community clear goals, while also generating excitement about AI's real-world potential. For example, improvements in image recognition translated into better medical imaging diagnostics and more reliable autonomous vehicle systems. The role of benchmarks illustrates how structured challenges can galvanize innovation in ways that abstract theory alone cannot. The evolution of natural language models followed a similar path, with researchers gradually moving from simple statistical methods to sophisticated neural architectures. Recurrent neural networks and long, short-term memory networks improve the handling of sequential data like text, enabling better translations and summaries. But the real breakthrough came with the attention mechanism, which allowed models to focus on relevant parts of input sequences. This innovation led to the development of transformer architectures, which could handle language tasks with far greater context and fluency. The transition represented not just a technical upgrade, but a paradigm shift, as attention-based models began to outperform older approaches across nearly every major benchmark in language processing. This progress set the stage for generative AI systems that could create text, answer questions, and even write code. The impact of transformer architecture cannot be overstated. Introduced in 2017 with the now famous "Attention is All You Need" paper, transformers quickly became the foundation for modern natural language processing. By allowing parallel processing of input sequences and emphasizing relevant relationships through attention, transformers achieved unprecedented efficiency and accuracy. They became the backbone of models like GPT and BERT, which in turn unlocked capabilities in translation, summarization, and conversation. Beyond language, transformers have been adapted for vision, audio, and even biological data, proving themselves as a versatile framework for diverse domains. The rise of transformers represents one of the most significant milestones in AI history, enabling generative models that captured public imagination and reshaped the technological landscape. Generative AI represents the latest wave of breakthroughs, with systems capable of creating images, audio, and text that rival human output. These models move beyond analysis into creativity, producing art, music, and written content. Public perception of AI shifted dramatically as people encountered tools that could draft essays, generate lifelike images, or compose melodies with a few prompts. While this has sparked excitement, it has also raised new concerns about authenticity, copyright, and misinformation. The ability of AI to generate persuasive content blurs the line between real and synthetic, making critical evaluation more important than ever. Generative AI demonstrates both the remarkable progress of the field and the new responsibilities it places on society to navigate the ethical implications of such powerful tools. Everyday applications of AI continue to expand, embedding themselves in ways that often go unnoticed. Recommendation systems suggest products and entertainment tailored to individual preferences. Voice assistants interpret commands and provide information on demand. Translation tools bridge language barriers in real time. These applications illustrate how AI has moved from research labs into the daily routines of millions. The ubiquity of AI highlights its dual identity, a cutting-edge scientific pursuit and a practical utility woven into ordinary life. For learners, recognizing AI's presence in daily tools makes the subject less abstract and more tangible. It is not just something to study in theory, it is something you already interact with, often without realizing it. Research cycles in AI have accelerated dramatically in recent years. Where once a breakthrough might take years to disseminate, ideas now spread across the globe in months or even weeks. Preprints, open source code, and collaborative platforms make it possible for researchers to build upon each other's work rapidly. Industry contributes by scaling innovations into products, generating feedback that informs academic exploration. This rapid cycle of iteration creates exponential growth, where each discovery builds on the last at an unprecedented pace. For learners, it means that staying informed requires ongoing engagement, as the field evolves faster than traditional textbooks or courses can capture. The acceleration of research reflects both the excitement and the challenge of participating in the AI era. International competition in AI has become a defining feature of the modern landscape. Governments around the world recognize AI as a strategic priority, investing heavily in research, infrastructure, and talent development. The United States, China, and the European Union are among the leading players, but many other nations are also shaping policies and contributing innovation. This competition drives progress, but also raises geopolitical questions about leadership, regulation, and cooperation. Just as the space race symbolized technological rivalry in the 20th century, AI now represents a frontier where nations compete for influence and advantage. Understanding this context helps learners appreciate that AI is not just a scientific endeavor, but also a global strategic challenge. The integration of AI with robotics represents another powerful trend. Advances in perception, reasoning, and learning are merging with physical systems, creating autonomous machines capable of navigating real-world environments. From warehouse automation to self-driving cars, the combination of robotics and AI expands the potential for machines to interact with the physical world. These systems require not only technical sophistication, but also safety, reliability, and ethical oversight. The merging of AI and robotics highlights the interdisciplinary nature of progress, drawing together engineering, computer science, and human factors. For learners, it demonstrates how AI extends beyond algorithms on screens into machines that share our spaces and shape our daily experiences. Shifts in academic research priorities mirror the evolution of the field itself. Funding and attention have moved from symbolic AI to statistical machine learning and, more recently, to deep learning and generative models. Each shift reflects both technological limitations and emerging opportunities. While symbolic AI dominated in the early decades, its struggles with real-world complexity led to exploration of probabilistic methods. Later, the availability of big data and powerful hardware made deep learning the focus. These shifts show how AI evolves in response to both successes and failures, reminding us that the field is not static but adaptive. For learners, understanding these transitions provides perspective on why certain methods dominate at different times. Competitions and benchmarks have consistently influenced AI progress. From chess and Go challenges to datasets like ImageNet, structured tests have provided motivation, visibility, and standards for measuring success. These benchmarks not only encourage innovation, but also shape research agendas, focusing attention on areas where progress can be quantified. For example, the ImageNet competition directly contributed to breakthroughs in computer vision by rewarding improvements in accuracy. Competitions also make AI accessible to the public, translating abstract advances into dramatic milestones that capture imagination. They serve as a reminder that progress is often driven not just by curiosity, but also by challenges that inspire creativity and persistence. Interdisciplinary collaboration has also expanded AI's scope. Fields like biology, linguistics, and neuroscience increasingly intersect with AI research, providing both inspiration and application. Biologists use AI to model protein structures, linguists study how machines process language, and neuroscientists explore parallels between brains and artificial networks. These collaborations highlight that AI is not a siloed field, but part of a broader scientific dialogue. The cross-pollination of ideas accelerates discovery, opening new horizons for both AI and the disciplines it touches. For learners, recognizing these intersections reinforces that AI is a tool and a partner across many domains, not just a branch of computer science. As AI has advanced, ethical questions have emerged at every stage. In the symbolic era, concerns arose about the transparency of rule-based decisions. In the age of machine learning, issues of bias and fairness came to the forefront. With generative AI, new worries about misinformation, authenticity, and intellectual property dominate. These recurring questions highlight that ethics in AI is not an afterthought, but a persistent theme. Each wave of technology raises fresh dilemmas while revisiting old ones, reminding us that intelligence without responsibility can be as problematic as it is powerful. Learners are encouraged to see ethics as integral to AI's development, shaping not only how systems are built but also how they are used. Looking backward and forward, the history of AI reveals a pattern of vision, challenge, and renewal. From Turing's early thought experiments to the rise of transformers, the field has navigated cycles of hope and disillusionment, ultimately achieving breakthroughs that once seemed impossible. Understanding this trajectory provides valuable context for present-day debates and future expectations. It reminds us that progress is cumulative, built on decades of exploration, setbacks, and perseverance. By studying AI's history, learners gain not only a sense of how far we have come, but also the insight needed to appreciate where we might be going. History, in this sense, is not just background, it is a guide to the future. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.